All right, I hope you're doing well. Let's go ahead and take a look at the topic of kinematics. Now, kinematics is actually one of the most interesting part of physics because it's actually a more of a tangible part because it's actually a topic that makes sense with our everyday lives regarding the motion of objects, how objects move, how much time does it take, acceleration, free fall, and all those topics. Kinematics is actually the study of motion. It's a part of classic physics that sort of talks about how much time does it take, for example, for an object to go from point A to point B? What's the velocity of that object during that time period, or what's the acceleration, and etc. Now, it actually derives from a Greek word, kinetikos, which stands for movement. Now, movement in general at our level is categorized into two levels. So if we were to kind of sort of have the meaning of the word motion here, motion is divided into either a constant velocity motion or B, constant acceleration. Now, there's different ways. Some books like call them uniform velocity or uniform acceleration, but nonetheless, they mean the same thing. Now, constant velocity is a type of motion in which the acceleration is equal to zero. Does that necessarily mean that the object has a speed of zero? No, the object could have had acceleration and then the acceleration could have gotten to zero. So it's going to just move at that constant velocity without changing its speed. Of course, that's an ideal situation because we know in the real world scenarios, if there's friction, there's air resistance, then the object definitely slows down. But nonetheless, whenever the acceleration is equal to zero, the only formula we can use is x equals to vt. Now, make sure you're already familiar with some of the topics. For example, x stands for displacement. You should know the difference between displacement and distance. Displacement is measured in meters and so is distance, but displacement is a vector quantity, whereas distance is a scalar quantity. V is actually the velocity of the moving object measured in meters per second, and t is the time taken, which is measured in seconds. Now, constant acceleration is a type of movement which is actually the prior focus or the main focus of this chapter. It's a type of movement in which the acceleration is no longer zero. In fact, it's a constant number usually. For example, the acceleration of free-falling objects on Earth is usually a constant number which is equal to the gravity acceleration due to gravity, which is roughly around 9.8 meters per second square. Now, for the ease of calculations, we usually round it up to just 10 meters per second square. And if we're throwing an object upwards, usually we take g to be equal to negative 9.8. And if the object is coming down, we take it to be positive 9.8. And the reason for that is when you're throwing an object upwards, the acceleration actually due to free-falling objects or due to gravity acts as a deceleration. It slows the object down. However, when you throw an object downwards, the acceleration acts in the same direction as the object, which is coming down, so it actually speeds it up. That's why it's a positive number. Now, constant acceleration divides into four different formulas. You probably will not need the proof of these formulas. The four most famous formulas you need to know for this part is number one, Vf squared minus Vi squared equals to 2a delta x. That's where Vf stands for final velocity, Vi for initial velocity, a for acceleration, and delta x the change in displacement. The second formula is Vf equals to at plus Vi. And the third one, x equals to 1/2 of at squared plus Vit. And finally, the last one, number four, delta x stands for Vi plus Vf divided by 2 times delta t. Now, a lot of you might be wondering, what exactly is delta? Delta in physics is usually the change in a quantity. For example, here, delta x stands for the change in displacement. So the final displacement of, for example, an object minus its initial displacement. It's like a car usually starts at a specific location. Let's imagine this is a car. And then it ends at another location. So the initial location could be like on the x-axis, like at 2 meters, and then it ends on a final location of like 5 meters. So the change in displacement is how far you are from the origin, which is just your final position minus your initial position, which is just 5 minus 2, and that's just 3 meters. Now, the key to any kinematics problem is, of course, there's graphs and kinematics, there's a lot of other things, but the main focus that you should also get really good at is the word problems. And I've actually provided you some of the word problems that you might be required to know at the A level. Of course, there's harder problems, but these are just some basic problems that you need to be familiarized with, and then eventually move on to harder ones once you learn the approach of how to solve the problems. Now, number one actually says you have a bike that's moving at 4 meters per second. By the way, meters per second negative is the same thing as meters per second. The bike is moving at that speed and has zero acceleration. Now, right away, I know I cannot use those four formulas because it's zero acceleration. I have to go to constant velocity. There's only one formula for constant velocity, and that's x equals to v times t. So since the bike is starting to move at 4 meters per second and has zero acceleration, I can simply say the final velocity of the car or the bike, or just the velocity of the bike for the whole journey, is just 4 meters per second because the speed of it never increases. It has zero acceleration. How far will the bike travel in a 10-second time period? Well, we know again from the formula x equals to vt, if the speed is 4, if we multiply that by the 10-second time period, the displacement or the distance traveled is just 40 meters. Number 3 says calculate the acceleration in each of the following cases. Number A, V stands for final velocity and U for VI. It says you want to calculate the acceleration. Now over there, if you want to calculate the acceleration, you can just use VF equals to AT plus VI. So you can either rearrange that for A, which you will get VF minus VI over T, or you could just use the original formula for acceleration, which is exactly what we just got. But anyways, the answer is going to be 22 minus 8 divided by the time taken, which is 2.6 seconds. Let's do the calculations for that. 22 minus 8 is 14 divided by 2.6. That's 5.38 meters per second square. That's the unit of acceleration. Let's take a look at question number 3B now. For 3B, it actually tells us to find the acceleration of a ball that starts at rest. Now, usually, the key is for you guys to understand that whenever a question says something starts at rest, that means usually the object's initial velocity is 0, or if something's dropped, for example. So VI is equal to 0 in B. It says after 30 meters, that means delta X is 30 meters. The final velocity of the car is 4.8 meters per second. So we're looking for, again, acceleration in the second part as well. We have to take a look at the formulas we can use. We have V final, we have V initial, and we're looking for acceleration. So the only one we can use is VF squared minus VI squared equals to 2A delta X. Now, VF is 4.8, so that's going to be raised to the power of 2. V initial is 0, so 0 to the power of 2 equals to 2 times acceleration times 30. Now, 4.8 squared is just 23.04, and this equals to 60 times the acceleration. Now, this part is just algebra. 60 is getting multiplied by a, so in order to get rid of it, we have to divide both sides by 60. So the acceleration is just 23.04 divided by 60. That means the acceleration is 0.384 meters per second square. Number 3C, it says a train moves 100 meters from rest. Again, we know the initial velocity is 0 in a time of 15 seconds, and it moves 100 meters. So we know the displacement is 100 meters. So again, if we go back to the original four formulas that we had for constant acceleration, the only one that we can use apparently here is, because if we were to kind of investigate the formulas, we cannot use 1 because we don't have final velocity, so that's off the hook. Number 2 is also not possible because we don't know final velocity. The only one that we can use, as it turns out, is 3 because we can use that one to find, we have x, we're looking for acceleration, we have time, and we have VI and t again. So we can use the third formula. That means I can write over here, we have to use the formula x equals to 1/2 of AT squared plus VIT. So I think as we're doing the problems, it becomes clearer and clearer that you just have to write the data down and then figure out the type of formula that you have to use in kinematic questions. So 100 is equal to 1/2 of acceleration times by 15 square plus 0 times by the 15. Well, 0 times 15 is just 0, so you'll have 100 equals to 225 multiplied by 1/2 multiplied by a. 15 squared is 225. All right, so 225 should get divided by 2, because that's what happens when you multiply 225 by 1/2. You just get 225 divided by 2. And that gives us 112.5. So 100 equals to 112.5 times acceleration. In order to find acceleration, we just have to divide both sides by 112.5. So acceleration is simply 100 divided by that. And the answer is 0.88 meters per second square. That's it. So that's going to be the answer for this question over here. The acceleration is found. Now, there is, of course, a lot of room for practice in this chapter. You have to have a lot of good algebra skills, for example, the rearranging parts as well as the division stuff. But you also need to practice a lot to get really good in the problem-solving parts. But for now, I think this is good. Best of luck. Goodbye for now.